Okay, this is an example of a PNP emitter follower. We can see we have an emitter resistor. We have the output on the emitter. Notice that it's a PNP because the arrow is pointing in towards the transistor. Our gain is 90. Our source voltage is 9 volts. Our base voltage is 3.9 volts. Our emitter resistor is 1K, and our time varying input signal that will be added at the base has an amplitude of 3 volts and 1 kilohertz. And we're not going to worry about the time varying input signal at first. We're going to first start with our DC values. So if you look at the question, it says on the graph paper provided, and we're not going to use graph paper, we're just going to draw a graph. We're going to draw a graph of the load line for the circuit. And we'll show how we're going to do that. We're going to calculate our values for voltages and currents, and we're going to then show where on the load line we're operating, and we're going to draw in some characteristic curves. We're going to see what the voltage gain of the circuit is, and that's going to be that for this one. So I'm just going to bring us over to OneNote. Okay, so here's our problem. The first thing we're going to do is, let me see if I can move this over. Yeah, there we go. We're going to draw our graph. So our graph is going to look like, let's see, like this, where we have IC on the y-axis in milliamps, and then we have VCE in volts is going to be on the x-axis, and we're looking for our load line. And so remember, our load line really shows us our limits of how our circuit operates, and it's limited by the DC components, the resistors that are attached to our circuit. So what we want to do is we want to think about cutoff and saturation. So our cutoff situation helps us to define what our max VCE is. And so remember, if we have V, we have our RE, we have our E, and we have our C, and then this is connected to ground. And in this situation on cutoff, our E is going to be equal to 9 volts, right? It's going to be the same as our source voltage because there's nowhere for the current to flow since this is not connected. And our collector is going to be at 0 volts. So when we subtract them, actually EC in this case, since we're traveling, the current is going down from E to C. So let's make this EC. Our value is going to be 9 volts. And now so this cutoff tells us that it's equal to 9 volts, and then saturation gives us information about our collector current. So again, we have V, we have our RE, and this is RE over here too. This is our E, this is our C, this is connected to ground. And so now remember, for saturation, we are saying that there's a wire from E to C. And then what we do is we want to calculate our IC in this situation, the max current I can possibly have if there's a wire connecting E to C here. That's the max we could have with the power source we're given. And so that's going to be V over our RE. And in our case, that's going to equal IC is equal to V over, so let's see, let me back up. So we're going to plug in 9 volts. 9 volts over 1K, and that gives us IC is equal to 9 milliamps, or 0.009 amps, which is going to be 9 milliamps. So over here I can draw 9, and it's in milliamps, and then that's what my load line is going to look like, just like that. Great. So now we know this is an amplifier, right? Where this is an emitter follower, and we have this our graph, and we're going to have characteristic curves, and so we know this is not operating as a switch. So we know we need to do some calculations. We know for our model, we're going to be pretending that there's a resistor in here, and the resistor is going to be controlling the current that's going through our emitter to collector portion of the circuit. Okay, so let's start calculating our values here in B. So we've completed A, and so we're moving on to B. So let's see, the first thing I want to do is insert a table. I think that's what I want. So let's see. Okay, there we go. Let's see if I can move that down. Maybe. See, undo. Here, I think I can add in some extra white space, maybe. Oh, we'll just add it down here. Yeah, there we go. Okay, so we're going to insert a table. There we go. Okay, so we're going to go back to draw, and this is going to be VB. We already know VB. VB that they tell us in the problem is 3.9 volts, so that's an easy one. VE, VC, VCE, or VEC. Let's fix that. VC, IE, IB, and IC. Okay, and we know now that looking at this, our PNP transistor, we know that the current is going to be flowing from the emitter into the base. And so we know that the base has to be 0.6 volts lower than the emitter. And so that tells us that the emitter is the base plus 0.6 volts. And so that's going to equal 4.5 volts. So right here, we know that this voltage right here is going to equal 4.5 volts. Okay, so the next thing we want to do is we want to figure out the current that the current IE, the current through the emitter. And so what we need to do is we need to figure out the voltage drop across this emitter resistor. And so how do we know the voltage drop? Well, that's just going to be V minus VE. And so that's just 9 minus 4.5. So if we want to calculate IE, we need to calculate V minus VE over RE, and that's going to equal 9 minus 4.5 volts over 1K. And so IE then is going to equal 0.0045 milliamp or amps. So so in here we're going to say that this is for all of our currents from here to here, we're going to say this is in milliamps, our units. So this is going to be 4.5 milliamps. Okay, so how do we calculate IB? Well, we know that IE is equal to IB plus IC. And we also know that IC is equal to beta, the gain, the current gain, times IB. So we're going to plug this in for IC. So we're going to get IE is equal to IB plus beta IB. We can then factor the IB out. So IE is equal to IB times 1 plus beta. And now we're solving for IB. So we divide both sides by 1 plus beta. So IB is equal to IE over 1 plus beta. Okay, so when we do that calculation, we get 4.5 milliamps divided by 91 because beta is equal to 90. So if we go to, let's see, go to MATLAB, we can do a quick calculation in MATLAB. And so we can say 4.5 divided by 91. That's 0.0495. So IB is equal to 0.0495 milliamps. Put that in my table. 0.0495. And now we want to calculate IC. So IC is equal to beta times IB. And so that's equal to 90 times 0.0495 milliamps. Again, I can go back to MATLAB and just do a quick calculation here. So I can say answer, because I know that that's my IB, and then times 90, 4.45 milliamps. So IC is equal to 4.45 milliamps. 4.45. Okay, so now that I know my IC, let's just look at my circuit again. Oh, I do know my VC. So looking here, this spot is my collector. So this is VC. This spot is right here. This spot right here is my emitter. This is VE, and my base is already marked. So VC is connected to ground. So I do know this. This is 0 volts. And then VCE or VEC is just 4.5 volts minus 0 volts. So this is 4.5 volts. So therefore, I've got all of my voltages and currents. Now it's asking me where on the load line am I operating? And so let's go back to our load line and just look at our values. So we've got our values in our load line right here. And so we can see that my VEC is at 4.5. So that's like about halfway, 4.5. And my IC is equal to 4.45, which is just about halfway here. So 4.45. Right, so I'm operating right around there, and that's where I want to be operating, around halfway. And then my IB is at 0.0495. So if I were to draw my the characteristic curve, I'm going to get something that looks like that, right? And so my IB is going to be 0.0495 milliamps, and that's around 50 microamps for that problem.